Hi, Professor Haldane. As someone who has shaped the way of how we think about condensed matter physics and trained the generations of physicists around the world, if you were to look ahead at the next chapter of the School of Physical and Mathematical Sciences at NTU, what aspiration would you have for the school in terms of the kind of scientific questions we should pursue and as a kind of global impact we should strive to make?
Well, I think the main thing is to be flexible and be ready to move onto some new area, when it appears to become important, and may basically take advantage of discoveries that science brings forward. So, for example, there's a lot of work on these moire materials, which are two-dimensional van der Waals bonded layers, which you can peel off. They're kind of, original one was graphene, but now the same principle has been applied to lots of other materials, and there are lots of promising possibilities that, because this builds structures on a scale which is much larger than the atomic scale by these moire interference patterns, and well, that's one of the surprising developments in recent years. But basically, I think we're going to have a lot of new developments in quantum materials, and that's certainly one of the areas I would hope that NTU is ready to move into. I mean, they already are moving into it in quantum technologies in a big way right now.
Okay, thank you. So 2025 marks the 20th anniversary of SPMS, a milestone that invites reflection on both achievements and future directions. From your experience mentoring young scientists, what qualities and culture do you think a leading school like SPMS must cultivate in its students and faculty over the next 20 years to remain at the forefront of discovery and innovation?
I think the main thing is to encourage independence of the students, that they try to introduce their own ideas into the research program, and not just follow what their professor tells them to do, but they should try and make sure they understand what they're being told to do, and they should be encouraged to contribute their own ideas, even if those ideas are wrong. They should be able to bring them up in the group meeting and have good discussion. And I think, to give people the confidence to propose ideas, and if you propose a wrong idea, you should not be ashamed, right? You should, once it's to propose it and discuss it, because sometimes even what sounds like a wrong idea turns out to be a fruitful idea. And that's the main thing, I think, in scientific research too, that the researchers are kind of encouraged to follow their noses for what is a good problem. Yeah.
Thank you. Very good advice indeed. Many of our SPMS students nowadays are still at the early stage of their scientific journeys, navigating uncertainty about research directions and careers. Looking back at your own past, including moments when the importance of your work was not immediately obvious, what advice would you give them about choosing problems to work on and having the confidence to pursue ideas whose impact may only be recognized much later?
They should choose a mix of problems. They should certainly choose problems that they can be passionate about, that they're kind of very interested in, and the opportunity to look at an area where something new has been discovered, a new range of experimental, and the region in which you could do experiments. Whenever you think a new area has been opened up, that's a very fruitful place to look for unusual and interesting new things. But of course, they should also, not be unrealistic. They should make sure they're working. Make sure they're working on a project that will eventually finish, right? Yeah. And but the one thing to remember is you don't know whether most people are not going to go on and be in a university or a government research lab. So the scientists, once they're trained, they should be able to find employment where they can make very useful contributions throughout the economy. And I think, having done a PhD and created a thesis and matured from just a master's student to a doctoral level, I think the maturity you get in understanding how to choose problems will be useful, even if they don't stay on. So you don't know what's going to happen in your scientific career, but you should follow what you think is what your heart tells you, but be ready. But realize that maybe you have to find other area to go into after finishing your PhD. And I think you'll be able to find a useful place to contribute to society.
Okay, so those are the three standard questions. Mm-hmm. If we have more time, when we just can comment, I don't know, shall we ask more questions for the interviews? Maybe I'll say ask a question. SPMS is a rather new department. This is the 20th anniversary. Comparing to many other universities, a very young department. And you have visited SPMS quite a number of times. So what are the main impressions of our department comparing to some other places around the world?
Well, it seems to be, activity seems to be kind of growing very rapidly. I see lots of initiatives, like a quantum initiative, and so I'm wondering how much the science and the mathematics get integrated, because there's also it's both mathematics and
physics.
And physics, yeah. And I think different cultures have a lot. I mean, it's a very useful thing to be able to get collaboration between different branches. So collaboration, if you can involve mathematicians and get them interested in the kind of, if there's some mathematical aspect to the physics problem, I think that's a good thing. But I can certainly see that the department, the school seems to be becoming very active.
Very active.
Yeah.
Thank you. Other questions? What advice do you give to SPMS? I mean, it's sort of like part of the question already. Maybe you can just say more and they can just add it.
Keep an eye out for whatever new is happening, and
more exchange, more interaction.
Yeah, and be ready to move into new areas when it looks like they're becoming important.
Okay, thank you.
A very good evening, ladies and gentlemen, and a warm welcome to the IAS Lee Kong Chian Distinguished Professor Public Lecture. We are very happy to see so many of you here today. My name is Cashro Tang, a third-year NTU student under the Faculty of Chemistry. It's an honor to be your MC for today's public lecture. This lecture is organized by the Institute of Advanced Studies at Nanyang Technological University with the support from the Lee Foundation. The fundamental laws of the field of quantum studies have remained constant for a century, and we are currently experiencing a second quantum revolution driven by a deeper mastery of its most mysterious properties, specifically quantum entanglement. This has been experimentally validated and is now recognized as a foundational pillar of the next generation of advanced technologies. Now, before we begin to commemorate this wonderful lecture, we will be taking a group photo of everyone. You don't need to do anything, you just need to sit up straight and give us your brightest smile of the day. Yes, the day has ended, about there. We're going to give you a brightest smile, okay? Just sit up straight, brightest smile, our cameraman will work for his magic. All right, good job, everyone. Now, to begin, may I invite on stage Professor Chian, Director of the Institute of Advanced Studies at NTU, to deliver his welcome address. Professor Sam, please.
Good evening. I'm very heartened to see so many of you today. I'm especially proud that we are able to bring quantum mechanics into the heart of Singapore's central business district. So let me begin with the formalities. Professor Duncan Haldane, 2016 Nobel Prize in Physics, professor at Princeton University. Our guest of honor, Professor Shunsuke Chiba, acting dean, College of Science, and chair of the Board of Governance at the School of Chemistry, Chemical Engineering and Biotechnology in NTU, distinguished guests, colleagues, students, ladies and gentlemen. Good evening and a very warm welcome to the Institute of Advanced Studies IAS Lee Kong Chian Distinguished Professor Public Lecture. It is my pleasure to welcome members of the NTU community as well as guests from across Singapore and beyond to today's public lecture at the Stephen Ridey Auditorium here, right at the heart of Singapore's city centre. Hosting this event in such a central and accessible venue reflects our commitment to engaging not only the university community, but also the wider public as well. Now, it is my privilege to open today's lecture as we gather to reflect on one of the most profound intellectual achievements in the history of science, quantum mechanics, and more importantly, on where it's taking us next. Last year, 2025 was hailed as the International Year of Quantum Science and Technology, marking a period of intensified global attention on this transformative field. As that milestone year concludes, our focus is now turning to the broader implications and responsibilities that accompany quantum advances. Now, indeed, 2026 has been described as the year of quantum security, a moment where quantum ideas are no longer confined to theory, but are actively reshaping how we think about computation, communication, and the protection of information. Now, it is therefore fitting that today's public lecture takes place here in the heart of Singapore's central business district, where innovation, security, and technology intersect. Now, even a century after its foundations were laid, quantum theory continues to challenge our intuition while opening new pathways that will shape the future of science, technology, and society. Now, on a personal note, I'm also a physicist, so quantum mechanics is also very close to my heart, not only academically, but also on a very personal level. I took my first quantum mechanics class, and that was at that class where I met my wife. So quantum mechanics is in our family. Now, before I proceed, I would like to express our sincere appreciation to the Lee Foundation for their steadfast and generous support of the Lee Kong Chian Distinguished Professor Public Lecture Series. Their long-standing commitment has enabled the Institute of Advanced Studies to bring some of the world's most influential thinkers to Singapore, fostering dialogue at the frontiers of knowledge. Now, at the IAS, we create spaces where transformative ideas can be shared, challenged, and expanded across disciplines. We seek to bring outstanding scholarship to diverse audiences and to encourage conversations that connect physics with mathematics, engineering with computation, and fundamental theory with emerging applications. Now, by convening pioneers who have reshaped their fields, we hope to inspire bold thinking and new perspectives, particularly among students and early career researchers. Now, today we are honored to welcome a scientist whose work exemplifies this spirit of intellectual depth and originality. Professor Duncan Haldane, Nobel laureate in Physics 2016, is one of the most influential theoretical physicists of our time. His groundbreaking insights reveal that topology and geometry are fundamental to the behavior of quantum matter, ideas that have reshaped condensed matter physics and opened entirely new avenues of inquiry. As quantum science enters a new phase, with technologies moving from theory to operational reality and societal stakes continuing to rise, Professor Haldane's work provides a critical foundation for navigating the challenges and opportunities ahead. Now, it shows how deep theoretical principles can guide the next generation of quantum discoveries, including the pressing priorities of quantum security. Now, looking ahead to 2026 and beyond, the landscape of quantum science will be markedly transformed as advances in technology, security, and application reshape both research and society. Now, we are especially pleased to note that one of Professor Haldane's former students, Associate Professor Yang Po of NTU, the School of Physical and Mathematical Sciences, is with us today, and later he will moderate the question and answer discussion. We are also honored to welcome our guest of honor, Professor Shunsuke Chiba of NTU, as the acting dean of the College of Science and the chair of the Board of Governance at the School of Chemistry, Chemical Engineering, and Biotechnology. Professor Chiba is a distinguished leader in chemistry and chemical synthesis. He is internationally recognized for his innovative contributions to synthetic organic chemistry and catalysis. At NTU, his work has advanced both fundamental understanding and practical methodology in organic synthesis, enabling new reactivities and promoting efficient, sustainable chemical processes with impact across medicinal and material sciences. Now, to our students and young researchers in the audience today, I encourage you to take this lecture as an invitation to think deeply, to question assumptions, and to appreciate the power of ideas that may at first seem abstract, yet often go on to transform how we understand the world and the universe around us. Now, the advances we celebrate today are the result of curiosity, persistence, and the courage to venture into unfamiliar conceptual territory. Now, thank you once again for joining us today. I wish you a stimulating and inspiring evening ahead. Thank you.
Thank you, Professor Sam, for the very warm welcome today. With that, may I now invite our guest of honor, Professor Shunsuke Chiba, Acting Dean of the NTU College of Science and Chair of the CCEB Board of Governance, on stage for his opening remarks. Professor Chiba, please.
Professor Duncan Haldane, 2016 Nobel Prize in Physics, professor at Princeton University, distinguished guests, colleagues, students, ladies and gentlemen. Very good evenings. On behalf of Nanyang Technological University, Singapore, NTU, it is my great pleasure to welcome you to Institute of Advanced Studies, Lee Kong-chen Distinguished Professor Public Lecture. This lecture series reflects NTU's commitment to advancing scientific dialogue and fostering engagement between global leaders in research and our academic community, especially students and early career scientists. Through the Institute of Advanced Studies, so-called IAS, we create space where fundamental ideas are examined in depth and connected to emerging scientific and technological frontiers. It is therefore a particular privilege to gather here today to reflect on one of the most profound intellectual revolutions in human society and human histories, quantum mechanics, and aptly so on the occasion of its centenary. Following a year of global quantum awareness in 2025, 2026 this year now ushers in the International Year of Quantum Security, highlighting how the principles of quantum mechanics are being applied to protect information, strengthen communication security through post-quantum cryptography, and lay the foundation for emerging technologies. In this new chapter, we see not only the lasting impact of a century of quantum discovery, but also the transformative opportunity that lies ahead. We are honored to welcome a scientist whose work has fundamentally shaped how we understand quantum matter. Professor Duncan Haldane, Nobel laureate in physics 2016, is one of the most intellectual theoretical physicists of our time. His pioneering insights into the role of topology and geometry in quantum systems have transformed condensed matter physics and opened entirely new direction of research with lasting influence across quantum science and technologies. In his lecture today, quantum mechanics after 100 years, and the second quantum revolution today. Professor Haldane will trace the evolution of quantum thought from its fundamental laws to a deeper understanding of its most counterintuitive features. Concepts once regarded as philosophical curiosities, such as quantum entanglement, famously dismissed by Einstein as a stocky action at a distance, are now experimentally established and central to the modern quantum science. Professor Haldane will show how these ideas underpin the second quantum evolutions, in which uniquely quantum phenomena have become essential resources for new technologies. As we move into 2026 and beyond, these insights will increasingly shape scientific discovery, technological development, and social impact. In closing, I would like to express our sincere gratitude to the Lee Foundations for its generous support of the IAS Lee Chian Distinguished Professor Public Lecture Series, and to Institute of Advanced Studies for organizing today's event. I hope this lecture deepens your appreciation of quantum mechanics and inspires reflections on how fundamental ideas continue to shape science and society. Thank you very much, and I wish you stimulating, intellectually rewarding evening. Thank you very much.
Thank you, Professor Chiba, for opening our event today. Now let us get started with the public lecture. Before we invite our speaker on stage, please note that a Q&A session will take place after the talk. There will be 2 mic runners available for those in the audience with questions. All you need to do in a moment's time will be to kindly raise your hand and the microphone will come to you. Ladies and gentlemen, our speaker today is Professor Duncan Haldane, the recipient of the 2016 Nobel Prize in Physics, alongside 2 other recipients for their theoretical work on topological states of matter. The title of his lecture today is Quantum Mechanics After 100 Years and Second Quantum Revolution Today. Without further ado, let us warmly welcome Professor Haldane on stage with a big round of applause.
That the thing from you? Thank you. It's a pleasure to be back in Singapore and see that quantum mechanics is alive and kicking in Singapore. There's a lot of activity here, both at NUS and Nanyang. So I'm going to talk about entanglement. So what is entanglement? Well, to begin with, the laws of quantum mechanics, as you heard, the modern quantum mechanics was really discovered 100 years ago today, last year rather, and they stood the test of time. So the laws of quantum mechanics haven't changed since about 1932 when they were finally kind of put together. But, and of course, what's been happening more recently, lots of tests of quantum mechanics have really confirmed that the laws that we think hold do hold as far as we can measure them. And so until recently, the idea of quantum mechanics in the general public was probably the Heisenberg uncertainty principle. People said, you can't measure 2 things at the same time. And there was also a nice idea that says, quantum mechanics says you can leave the room by 2 doors at the same time. Basically, the principle of interference between different paths. And the famous Yogi Berra, who's a baseball player who was famous for his aphorisms. Exactly, when you come to a fork in the road, take it. Go both ways. Anyway, but that's older, but in recent years, entanglement has come to the front as probably the most fundamental and strange property of quantum mechanics, the central property. And starting around 1980, we've had new insights into quantum mechanics, and as was mentioned, topological aspects of quantum mechanics have become important. And at the same time, there was another evolution of ideas called quantum information theory, started by Feynman back in the late 50s and early 60s. Feynman started thinking about what would happen in the future as computers got smaller and smaller when they got down to atomic level. And to understand atoms, you can't understand atoms without quantum mechanics. So it was a total revolution. Before quantum mechanics was discovered, no one really knew what an atom was. They were vaguely thought they could identify them through Brownian motion and things, but there was no real basis for understanding matter before quantum mechanics. But Feynman thought that a quantum computer would be very useful for calculating properties of quantum materials, to understand the properties of materials, to design them and things. You really need to understand their chemistry, the chemical bonding, and you need quantum mechanical calculations. And he thought quantum computers would be very useful for calculating quantum mechanics. And probably one of the ideas behind quantum computers is they'll be used to simulate materials, but there's lots of other things that we have learned, for example, cryptography and the like. Okay, so what is quantum mechanics? So originally, in 1913, it started. I guess a bit earlier, Einstein himself and Planck came up with some of the early ideas, and the Bohr model of the atom was formulated around 1913 after Rutherford had discovered the nucleus of the atom. And the picture had emerged then of the atom was like a little planetary system with electrons orbiting around the nucleus of the newly discovered nucleus of the atom, like planets. But quantum mechanics forced the electrons to remain at special orbits rather than, and that was not explained, but it was an empirical rule that seemed to fit atomic properties. But around 1926, the modern version of quantum mechanics arose, and the notion of the orbit of Bohr becomes what we now call an orbital. So instead of electrons going around an atom like a little planet going around the sun, the orbit is a kind of fuzzy region which can be viewed as a box that can either contain an electron or not. And we don't actually know where the electron is, except either it's in the box or it's not in the box. And I'm going to use this notion of the box, which could either be empty or filled, as a model for the qubit, the elementary unit of quantum information. So Heisenberg's uncertainty principle turned Bohr's orbit into a kind of fuzzy cloud centered on the nucleus. And so we can think of atomic orbitals as boxes into which electrons are put. And this is a model of the simplest object, a hydrogen ion, which has lost its electrons, so the box is empty, or the hydrogen atom, which is neutral, where the box is filled. And so this is a very quantum mechanical idea, the two-state system, which turns out to be it's either empty or filled, 1 or 0. So we can actually now, we can't still see directly the orbit of the electron around the hydrogen atom, but we can image highly excited orbits of the thing, where instead of being in the lowest energy orbit, the electron is spread out, not in a kind of ring or a shell around the atom. This is a picture of a highly excited hydrogen atom. You can actually see the Rydberg orbit, the orbit in which the thing is in. And this is actually a device which is a system which is very promising as one of the possible platforms for quantum computing, because you can on this scale, you can address the electron in the Rydberg orbit with a laser beam, okay? Because it's much bigger than the original lowest orbit. And anyway, so I'm going to talk about the Pauli exclusion principle, which is basically gives you the essential picture of entanglement. Okay. So Pauli's exclusion principle is essentially one of the later innovations to be discovered in quantum mechanics, but it's central to everything we see around us. And I'll come to that in a minute. So as I say, in addition, electrons are special. They have a property that two electrons can't be in the same state, which roughly means that they can't be in the same place at the same time. And but electrons have this additional property. They're not just a particle carrying a charge. They have a spin, something called a spin. They're spinning like a spinning top. And we can put two electrons in the same box or same orbital, provided their spins are pointing in opposite directions, to satisfy Pauli's principle that you can't put two electrons in the same state. And so they can only go in the same box if their spins are in exactly opposite directions. And it turns out, quantum mechanically, you can think of this as one electron up and the other electron spin down. But it could actually be one electron spin sideways to the right and the other electron having it spin sideways to the left, just so long as they're in opposite directions. Things are happy, and there's this, Pauli tells you there's this minus sign. This is a picture of the quantum mechanical state of the electron. So it's both up. Electron 1 can be up and electron 2 is down, but at the same time, there'll be some probability that the first electron is down and the second one is up. And the minus sign means that means that I can't put up minus up because it would cancel. So this is the Schrödinger wave function of the electron, and we see this property of the electron being either up down or down up. And this is the simplest example of an entangled state of two particles or two qubits. And it's a maximally entangled state because it's exactly a 50-50 mixture of two different configurations. So the Pauli principle, as I said, is actually the feature of quantum mechanics that we most directly experience around us. Because you might ask, why do I not fall through the floor? The floor is made of atoms, but the atom is 99.99% empty space, and it's not electrical repulsion or anything that prevents me falling through the floor. The reason that matter is stable and the normal force that Newton described, but as an empirical observation, you push down on something and it pushes back on you. This is actually all the workings of the Pauli exclusion principle. Because it's telling you that the reason you feel a normal force from the floor that resists gravity and stops you falling down through to the center of the Earth is that the electrons which are bound to atoms in your shoe can't be in the same place as the electrons which are bound to the atoms in the planks on the floor. And so you wouldn't have thought quantum mechanics explains the basic features of the world around us, but that is in fact one of the most central features, and it's Newton's normal force. And so we see that this Pauli principle is a very central part of quantum mechanics, even though it was only perhaps the last element in the puzzle that was added to the laws of quantum mechanics. So the chemical bond that binds us all together is interesting clusters which make us up, molecules that bind us together. This is actually a maximally entangled state. For example, the hydrogen molecule is held together because I put the two negative electrons in between the two positive electrons. And to be in the same place in this region in between the two nuclei to form a chemical bond, they have to be in this maximally entangled state, up, down, minus, down, up. And actually, this is perhaps from the chemist, up till recently, there hasn't been much quantum mechanics in chemistry. And in fact, this is probably putting electrons and atoms into boxes is probably the only thing that a chemist needed to know about quantum mechanics, at least till recently. And so here we see the chemical bond is an example of this quantum entanglement because it allows you to put the two electrons in the same place. And this is actually, it'll turn out to be the central theme of the kind of second quantum revolution. And we'll see in a minute that entanglement was pointed out, as was mentioned by Einstein. But he pointed it out because he thought it was so crazy. He didn't like the way quantum mechanics had developed, even though he made some of the important early advances in quantum mechanics. By 1935 or so, he felt quantum mechanics was so crazy it couldn't possibly be a valid theory of the world around us. It had to be an approximation to some true theory. But so he pointed out quantum mechanics has this entanglement property, not with the idea that we should use it for something useful, but it's saying it's so crazy it can't possibly be true. But now it's been well established, and instead of this thought experiment of Einstein, it's now being more and more viewed as a fuel, as something which is used to drive quantum information processing. And it's a resource. And, okay. So, this was the famous quote of Einstein that he pointed out the entanglement property, which he said was spooky action at a distance. Schrödinger, on the other hand, came up with a much politer word for it and said, let's call it entanglement. It's actually a very interesting word because every language seems to have adopted a different root word for entanglement. The French is intrication, the German is Verschränkung. I'm not sure what it is in Chinese, but there's no these words are not related linguistically. So it's interesting that entanglement is every language seems to have adopted its own special word for entanglement. Okay. So what was Einstein's criticism of quantum mechanics? It's again going back to the chemical bond. The chemical bond entanglement is actually not particularly special when it occurs on the atomic scale. Every chemical bond that's binding the molecules in your body together is basically an entangled structure. So entanglement on the atomic scale is everywhere. But what Einstein worried about was, suppose I could take this chemical bond and stretch it and stretch it and stretch it while maintaining this entangled property. Now, the short distance atomic scale chemical bond is very stable because it's protected by what's called an energy gap, another consequence of quantum mechanics. And a large energy gap prevents it from being broken. So to break the bond, maybe you have to go out in your skin, and the skin will be damaged if you go out into the sun by ultraviolet rays from the sun, because they're able to overcome the energy gap to break chemical bonds in your molecules. But when you stretch this thing, the protection, the energetic protection of the entangled state gets weaker and weaker. And so Einstein thought it was crazy that you could have this. Oops. Going the wrong way. What happened here? There we are. That if I stretch this chemical bond or this combination of two spins which were in a superposition of states up, down, and down, up, he said it's crazy. If you measure the direction of the spin, you can only You can measure it in any direction you want, because up, down, minus down, up is the same as right, left, minus left, right. If you make a choice of which direction to see if it's along this direction or along that direction, you will find that if you measure the other one, you'll find exactly the opposite answer. And he thought, how can that be? Because he thought that was a violation of relativity, that somehow if you measured this spin here, it instantaneously implied that any measurement of the other side would get the opposite result. It's actually not a violation of relativity, so nothing is actually traveling faster than the speed of light, because there's no information. What relativity tells you is that information can't travel faster than the speed of light, and the person looking at this spin has no way of knowing what the measurement on the other side was. And you can, of course, take this laser pointer, and if I point it on the surface of the moon, if I move it sideways, I can make this dot actually move much faster than the speed of light on the moon, but it's not actually transmitting any information from one point on the moon to the other point of the moon. So there wasn't actually any violation of Einstein's relativity principle in the idea that if you measure this one, any measurement of the other one will give you the opposite result. Okay. But anyway, this was proposed. It was someday in 1935. Einstein's collaborator Podolsky went to the New York Times and told them that Einstein has demolished quantum mechanics. And probably that was a day when there was not too much news, because no country had been invaded that day or anything, but it made the headlines of the New York Times that day. But Einstein was actually furious, because he said that the physicists should not be washing their dirty linen in public. He never forgave. He kept on collaborating with the other guy, Rosen, but he completely broke off with Podolsky for doing that. But anyway, so Einstein proposed a set of measurements which he thought would definitively prove quantum mechanics was wrong. Einstein's proposal, his thought experiment, was not technically possible at the time, but various other people, in particular John Bell, formulated them in a more fancier way to give you a more precise criterion for determining whether Einstein's ideas of local realism were correct or not. And Bell came up with a set of inequalities that basically said if you do a certain set of measurements, and if the answer you get for something is greater than a certain amount, the kind of common sense idea of the world that Einstein wanted could not possibly be true. They're called the Bell inequalities. And the Nobel Prize a couple of years ago was finally awarded for the people who in the end carried out these measurements. In particular, Alan Aspect was the final. John Clauser made the partial proof of the Bell's inequalities, showed that quantum mechanical was correct. Aspect did the later one. And so there's actually no doubt that the ideas that Einstein wanted to replace quantum mechanics are not correct, and quantum mechanics has won every test. But as I say, its entanglement over distances larger than the chemical bond is very fragile against decoherence. What Aspect did in his experiment, he didn't have electrons with a spin, but he used light. The photon has something like spin. The photon has two states. There's a polarization that your sunglasses get rid of the horizontally polarized photons which get reflected off the road on a hot day and keep only the vertically ones. But the photon can either be electric fields going up and down or sideways, or it can also have a so-called circular polarization where it's spiraling one way or the other way. So the photon is also a particle that can have two internal states of a thing, and so it's also a qubit. And Aspe then used modern optical fibers, and he carried out Einstein's experiment, or the proposed experiment, and showed that entanglement of photons can be produced over large distances. Started out over a few kilometers in an optic fiber under Lake Geneva, but recently in China it's been extended to satellites in orbit. So photons interact very weakly with the environment, especially if they travel in optic fibers. We see photons that are coming from shortly after the Big Bang, when neutral atoms formed in the early universe. The microwave background is photons which come from that thing, and they've reached us after 12 or 11 billion years without actually interacting with anything. So photons actually are very resistant to interacting with the environment, and you can produce this entanglement over large distances. Okay, so let's look at classical and quantum information. Classical information is basically a switch which is on and off. And one version of this switch is little magnetic things, like in the old magnetic tapes or the disk drive you had, a magnetic disk drive. You have little magnetic regions where all the spins are pointing one way or the other way, which are different ordering, magnetic orderings. So a classical thing is lots and lots of spins pointing up, and lots of spins pointing down to be either 1 or 0. But quantum mechanics is a single one. And the basic thing is, I said that you can choose which direction to measure the direction the spin pointing. What you measure is the component of the spin parallel to any axis of your choice. And as I say, the two independent possibilities for any axis are pointing one way or the other way. But it says the information in the quantum qubit is much richer than just up or down. It's actually a continuously variable parameter that can point, that's equivalent to pointing in any direction on a sphere. It's called the so-called Bloch sphere. So this is the image of the qubit. But if it was pointing in the North Pole, it would partially be in a mixture of states pointing around up this here and pointing downwards. So anyway, so we have basically characterized the spin by two complex numbers with a normalization. So basically three pieces of information, which direction, latitude and longitude or whatever, which direction on the sphere you're pointing in. So it's a much richer place to put information, but it's a much more delicate thing. So classically stored information is unaffected by reading it and copying it. In fact, it's actually quite difficult to get rid of classical information. If you want to recycle your computer and you want to take all your bank information off the hard drive, including bank information in files which are lost from the directory but not actually deleted, you actually have to do quite a lot of work to destroy the information. But the quantum information is much richer, but it's also much more fragile, and it's more easy to destroy. And finally, an important property of quantum information is you can't copy it. So people worry about violation of copyright, somebody getting hold of copying all the songs off the internet, and saying, "Oh, it doesn't matter. Each time I make a copy, no one's lost anything." But you cannot make a multiple copy of a qubit, and so you can't copy them, but you can do other strange things with them. You can do something called teleportation with the qubit. So these are some of the properties. No cloning property. We can't actually, if this is a qubit in a given state, we can't take a kind of arbitrary qubit in an arbitrary state and make it become equal to that. So I can't copy the qubit. So that's one of the central features in quantum cryptography and security of quantum information. You can't copy it. Or at least you can't copy it indetectable way. First, you could steal it, but you can't copy it. But what we can do is we can transfer the information from one qubit to a blank qubit at the expense of the information here is killed, but it's transferred to this other qubit. And this can be done over long distances. Like people think of teleportation as something from the TV series Star Trek and stuff, and science fiction. But here we actually have the thing, and this is one of the rationale for thinking of entanglement as a resource that can be used up, that should be created and can be used. Because if I create an entangled pair of qubits and manage to stretch them over a large distance without destroying the entanglement, for example, a pair of photons, what I can do to transfer the information in this qubit to the remote location is I can do a measurement of a joint property of both the left-hand qubit here and the target system. And this measurement, there are actually two states. This could be up or down, and this one could be up or down, so there are 4 possibilities. So I can do a measurement which has 4 possible outcomes to it. And I do this joint measurement, and then to communicate, then to send the information elsewhere, I can pick up my telephone and do what's called classical communication and tell the person at the other end of the formally entangled pair is which of the 4 results of the measurement I found. Then he or she can do something to an operation on the qubit at their end. He can do one of 4 possible operations, depending on what the result of the measurement on the left side was, and he will then reconstitute exactly whatever the state here was. So no one ever found out what the state of the qubit here was, but now it's been teleported over a long distance, but it's not a violation of relativity because the speed of the telephone communication is limited by the speed of light, right? And at the end of this thing, the information which was here locally has been completely destroyed, but it's now the qubit itself is pushed over here. So anyway, this leads to this idea of entanglement as a fuel for quantum information processing. So one thing is, how do we actually produce entanglement? So it turns out any 2 systems become weakly entangled if I bring them together and allow them to interact. And this maximally entangled state is called a Bell pair after John Bell's analysis of this situation. And we want to actually create these Bell pairs because they will be the resource for carrying out any kind of quantum computation or quantum cryptography. So as I say, in the chemical bond, the Pauli principle kind of forces entanglement on you, but it doesn't work for remote objects. So to make an entangled Bell pair, I can start with 2 qubits in a known state. And the conventional way to do this is to bring them together and allow them to interact. And this is often called a gate. So you interact them with some gate, and gradually, as a function of time, while they're in contact, the state will evolve from being up to this up down and minus down up. So if at a precise time, this state under this interaction will have turned into this, and if I then switch off the gate at exactly the right time, I'll have produced a perfectly entangled pair. Now, it's very difficult to turn it off exactly at the right time. There's some ways to slightly correct and do that, but it's rather a delicate operation with these gates. And when I discuss a bit later topological quantum states, they, on paper at least, have the possibility to replace this delicate procedure, which has to be carefully managed with a robust one. So what I learned recently I was at this Global Young Scientist Summit organized here in Singapore, and we had speakers from there was a a quantum company called Continuum, who's actually setting up a lab here in Singapore. But they have a nice thing. They have these ions which can contain the quantum information for a long time, and they do quantum computations, or they attempt to do quantum procedures by bringing these ions that are on a racetrack, a bit like at the dry cleaners, where the suits have gone into something. They bring in ion number 141, bring it together with ion number 32 for a precise amount of time with this gate, and then they separate them and send them on their way. So this is a thing where they're actually attempting to, let's see, here's my thing. Attempting to do this gate procedure by actually bringing things together. But as I say, we'll see that there's actually maybe some way to do this without such a precise, such a delicate and fragile operation. So the cryptographic uses are sort of already with us, not the computational uses. So there's actually, you can now buy equipment for key transmission, for transmitting public keys from one place to another in a way that you can know that they haven't been overheard. So to actually transmit this kind of quantum information, which the no cloning theorem is a kind of guarantee that the eavesdropper can't intercept or wiretap your information during transmission without detection, because it would just, the act of trying to capture it would destroy the information. So you'd know you're being listened to. So to do this procedure, you actually don't use teleportation. They actually transmit the qubit itself, because light, the photon, is a qubit. It's got these two states in its polarization state. And so you can just send light, but it turns out you have to send it one photon at a time. So the way the crucial thing for cryptographic usage is so-called a single photon source, where you have there's a lot of work with like pulsed light sources, but now this is a pulsed light where the pulsing is so weak that there's at anyone in the time, the window with which you do the measurement, only one photon is present. So this is still quite a difficult thing to produce, but there's a lot of work going on to try and build single photon sources, which are the ideal thing for quantum cryptography. Laser, on the other hand, you have lots of photons in exactly the same state. So a kind of weaker version of this is to use a laser beam, because you can transmit the thing. But there you have more than one photon in the same state, and the eavesdropper could capture one of those photons and get the information. And all you'd know was that your signal was slightly weaker because it was one less photon arrived than you expected. So if it was a very, very, very weak beam, you might be able to detect that it was being overheard. But basically, the key thing is the photon itself is the qubit, and you need this kind of single photon source. Okay. Anyway, so let me move on to topological things. So around about 1980, condensed matter physicists thought they knew everything. They thought they were just going to tidy up a few details. They studied magnetism, they studied electron metals and helium liquids. So lots of things were known, but whenever people think they've got most of the stuff nailed down and understand everything, something comes along, an experimental comes along to show that they really understand nothing. And that was what was happened when the quantum mechanics itself was initially discovered at the beginning of the 20th century by Planck and people. People thought, they didn't quite the only thing they didn't really understand was atoms, but they thought, well, they knew everything else. But when the atomic properties were kind of started to be seen more systematically, and quantum mechanics emerged. All the kind of satisfaction with classical electromagnetism and everything from the previous century went away. Okay, so independently around 1980 two weird properties, which is one thing I discovered theoretically, but the most important one was von Klitzing's discovery of the quantum Hall effect. These were kind of two completely unanticipated things. So the most interesting experiment discoveries are things that people come across kind of accidentally. I never expected to find what I found, and von Klitzing never expected to find what he found. And in fact, as we'll see, they turned out to be weird, and they didn't fit into the ideas of the time because they were kind of condensed matter which quantum entanglement was playing a more important role and hadn't been thought of at that point. Okay, so what is topology? Topology is actually just attaching a number to something, an integer, a whole number. So if I can describe some state of matter and say it's characterized by the number -2, and some other normal matter is characterized by the number 0, I've got to have a boundary between these two regions. I can't go continuously from -2 to 0. And it turns out that a lot of interesting things happen on the boundaries of these systems, and the boundary is somehow there because there's some entanglement in this structure which can be characterized by this number. The topological properties of materials, they can't change continuously. This makes their properties robust. So a small amount of, which is again, contrast to our current silicon technology, which is based on ultra-clean wafers of silicon. These people in the fab here are dressed up in these spacesuits, not so much to protect them from the noxious chemicals that are being used in this process, but to protect the silicon wafers from contamination by the workers, because a little bit of dust or piece of hair or spit or something on the wafer would kind of ruin it. So the current technology requires ultra-clean systems, but anything that's based on topology has some kind of robustness, because you can't change this integer number immediately. This is actually why this is why it's kind of useful for quantum information. It helps to protect the quantum information, because if it's protected topologically. And the classic example of that is the number of holes in something. Like a donut has one hole, while a football has no holes. And holes are whole numbers. You can't have 0.36 of a hole. You either have a hole through it or you don't, at least on a scale much larger than the atomic scale. Okay, so this is this kind of classification of system by holes, and people giving lectures, physics lectures about topological stuff, can't resist from showing a movie of a coffee cup turning into a bagel, because they're topologically the same thing. Okay. So topological states of trivial states of matter are kind of just bring the atoms together and stack them next to each other and put them in contact. They get weakly entangled from the contact, but they're not entangled in a fundamental way. But if something changes at some point, as I bring these things together, the electrons which are living in these separate little boxes on each atom can get rearranged in an interesting way and to form chemical bonds, and something discontinuous happens at that time. So the simple example, which seems really remarkable that they gave me a Nobel Prize for this, but there's some other work too. But this is a kind of spins in magnets, in a rare earth magnet, which are very topical because the rare earths are an important resource. The large magnetism of rare earths is because they have sets of orbitals, sets of boxes in which the spins want to go in parallel to each other. Before I put a second spin in box 1, I want to have all the boxes have spins parallel. So these spins add up. So a very large magnet has got lots of individual elementary magnets, the spin of these electrons all lined up, and we call the spin of electron 1/2 for various reasons. But so if S is a number, So this is S equals a half, spin 1, spin 3 halves. So we see that actually 2s is a whole number. And it turned out to be that was topologically significant in some kind of states. And the simple view of magnetism at the time I started my work was that you just lined the atoms up and brought them close to each other and just made their spins point in certain ways. This is something called an antiferromagnet. If it picks up a paper clip, all the spins on each atom have to be all pointing the same way. This is one where the spins alternate, where they're up, down, and this is a spin 1 line of a spin 1 chain of atoms. It turns out that the quantum mechanics can allow these things to, the spin 1 can somehow break up into 2 spin halves and form a kind of entangled bond with its neighbor. And remarkably, you get something like this, and then at the end of the day, there's a half of a spin 1 left over at either end of the chain. And this was a kind of turns out to be an example, was actually one of the earliest examples of a topological state. And you can see that something unusual is happening at the end, because all these spins were this, spin 1, but now I ended up with a spin half separated and a half integer spin here. So these nickel atoms, this is what it had all spin 1, but there's like half of the spin on one side and half the other side, which is the boundary between the topological matter and the non-topological matter. So this actually at the time was very controversial. I don't really understand why, but it didn't match the conventional wisdom about magnetism of the day, and it generated a huge controversy. I was blocked from publishing by referee reports for quite a long time. A senior person stood up at a meeting I was at and said, "I'm not listening to this, it's nonsense." Not nice things to do to postdocs. But anyway, it led to a controversy, and controversy is really great for science, right? I mean, then it got a lot of people interested on one side or the other, and people came up with new ways to make new materials to actually build these chains of atoms to see what they would do, and others came up with new theoretical ideas. And it turned out that this actually had a profound impact on future developments in condensed matter. And underlying it, when the topology came out, it really led to a new way of thinking. So that's really why it turned out to be strange. But anyway, so looking at so for students and things, this was unexpected to me, and because I looked at it from a different viewpoint from the conventional way that the magnetism community was looking at it. And sometimes when you're standing from a different perspective, you can see something that the conventional wisdom hasn't. Anyway, so this was so people made materials like this, the chain of nickel atoms, and of course I'm only here today because it turned out that my predictions were right. I wasn't always sure they were. I was forced to the conclusion that the conventional wisdom was wrong without even wanting to do that. And but anyway, so there's a controversy. And I'll come back to this quickly at the end. The meme here is that you've got something funny happening, rearrangement happening, and you've got half of something, half of a spin 1 at one end of the chain and half at the other end. One of the ideas for topological quantum computing is very similar to this, but much more remarkable. I'll come to that. Okay, so this is my certificate. This is anyway. This is somebody else's model of what I found, but a simplified version that's very easy to understand. So if I'd known the original, if I'd come across this version of the model, maybe my paper wouldn't have been rejected because it was so obviously correct. But anyway, later people found a way to rationalize this to make it completely obvious, even though it wasn't at the beginning. So the other thing which I'm going to mention is something called the quantum Hall effect. The other thing which was discovered there, the weird thing was that you measured some electrical property of a semiconductor, and you found on this thing, you find as you lower the temperature, it gets stuck at these plateaus where the conductance, or actually measuring the resistivity, the whole resistance, but you end up with these perfect multiples of e squared over h, which are fundamental. This is the charge of the electron and Planck's constant. And here just an integer and the whole number. And initially people say, well, are there going to be any relativity corrections to this thing? Because it turns out, no, not at all. This thing is a topological effect, and so long as the system is bigger than a certain microscopic length scale, this number comes out perfectly. And this is such a precise thing that von Klisting discovered, there's his medal, that it's actually replaced, it's democratized the system of weights and measures. In the past, it was French, I guess Napoleon introduced the metric system, and anyway, the kilogram was a lump of platinum sitting in a safe in Paris, and if you wanted to kind of compare your weights to the official kilogram, in principle you had to go to Paris, knock on the door and say, can I compare my kilogram to the official kilogram? Now with quantum mechanics, this in combination with another thing called the Josephson effect allows you to build a quantum device which will reproduce the new official kilogram, which is based on e squared over h and e over h. Without anyone in any country can have their own version of the kilogram, and they'll know it's going to be identical for each country. There's no kind of French imperialism here. So the quantum Hall effect was not initially understood to be topological. It involves electrons which go around in a little magnetic field. They go around in circles. There's a magnetic field pointing towards you, but they're confined to a two-dimensional surface. But one of the things you see from this is if they're going around little circles and not moving, if the circle is too close to the edge, it won't complete a complete one. It'll go bounce, bounce, bounce. And one of the strange things of the quantum Hall effect is that you have a current which is traveling one way around the edge, like a one-way street. It depends on the magnetic field direction. If I reverse the magnetic field direction, the current travels the other way. And it turned out that there's a kind of system called the highest occupied orbital and lowest empty orbital, the Fermi level. So long as the Fermi level sits in a region between this energy gap, you will measure this precise thing. So von Klisting's measurement was again a luck that he put his sample he put a constant current through his sample, put it in a magnet which he switched on, and each time he switched on the magnet, the voltmeter showed exactly the same number to 4 or 5 significant figures. And of course, first he thought the voltmeter was wrong, but then it was broken in some way, but then he found that was a real effect. And it was amazing. No one would have dreamt that could happen. A Japanese group did essentially the same experiment some years earlier, but they put the system in a constant magnetic field and then switched the current on. They never get to exactly the same current, so they never see the same voltage, so they never saw this effect. So again, it's the luck in how you design your experiment, even if you didn't realize there would be an important difference between doing it at constant current or constant magnetic field, is the kind of thing that allows regular people to make amazing discoveries, right? Okay, so this is even later than this was now the Hall effect became the fractional quantum Hall effect, where the number was not e squared over h times an integer, but a fraction, like 1/3. And Dan Sui, the guy who found this experimentally, at that time people had just come to terms with the idea that this measurement should give you e squared over h times a whole number. So he realized, well, that must mean you have fractional charge. If you want to write this as a whole number times some charge squared over h, in this case, with a 1/3 quantum Hall effect, it told you had to have 1/3 charges floating around, which is again a totally unexpected thing at the time. This is the device in which the fractional Hall effect was first measured. It was actually built by this guy, but only 3 people can get a Nobel Prize. So the people who measured it and then the theorist who explained it got it. But you can see that you wouldn't get a job at Intel if you showed that as a proof of your soldering ability, right? So you can see how the topology is actually, you don't need a perfectly clean, perfect system. The topology is very forgiving. It kind of, it allows some degree of imperfection, and the effect is still there perfectly. Okay. So in this Laughlin state, it turns out the weird thing is that instead of each electron occupying 1 orbital, as it does usually, it occupies 3 orbitals. And the repulsion between the electrons likes it to do that. So this weird state that Bob Laughlin discovered. And so it turns out that if the central orbital is empty, it generates 2 empty boxes around it to reduce the Coulomb interaction between the systems. And then it has this weird thing, if I pull the electron out of it, the 3 orbitals which were somehow surrounding the electron, once the electron is gone, they don't want to stay together, and you removed 1 electron, but now they split up into 3 independent parts, and you get this weird thing of fractional charges floating around. Again, sort of strange things that quantum mechanics allows. And so these fractional things also have something called fractional statistics. Usually when you exchange a pair of electrons, you'll get a -1 sign. If you exchange a pair of photons, you get a +1 sign. It turns out if you in this 2-dimensional thing, if I braid them around each other, you exchange them, which has to be done in either clockwise or anti-clockwise fashion. So it's like braiding hair or something. They get complex number phases, which are not just +1 or -1. And again, this fractional statistics and fractional charge have finally been kind of proved. The fractional charge, you can hear what the charge of the electrons is if you by listening to noise. If it's raining, as it does here often, and if it's raining on a tin roof, then if the raindrops are big, you hear one kind of noise, and if the raindrops are tiny, you hear a much higher hissing noise, right? So by listening to the kind of the noise, you can work out what size the charge carriers are. So, and later on, more sophisticated things we're doing to actually prove you have this weird statistics. Okay, let me just move on. Around that time, it became clear that you didn't need a magnetic field to produce these quantum Hall effect. Something else. The second thing I did, which I suspect was the real reason I got the Nobel Prize, but I also accidentally discovered that you could get regular crystalline matter with magnetism could generate these kind of quantum Hall systems, and this led to a lot of new stuff, which I'll come to. So these systems without a magnetic field that show the quantum Hall effect require you to have flat bands, very little kinetic energy, because in the Landau level, the energy of the electron doesn't vary with position. It doesn't have any kind of kinetic energy. And these flat bands you get more recently with graphene sheets. There's something called Moiré systems, which is a big new thing that people are working on tremendously these days, is by taking 2 sheets of graphene, you can make these kind of structures which are not atomic scale structures, much, much larger than that by just twisting the 2 sheets of graphene. You can see the picture here. And it turns Manipulate the quantum information. Okay, we're back. Okay, so this is the attempt to make a quantum qubit which is hidden from the environment and it has a much harder time in losing its information. And it's actually at the heart of one company among all the others has gone into this in a big way. Microsoft have been trying to build this thing. They announced their architecture, but they haven't actually announced, as far as I know, the working qubit yet. But on paper, it's a great scheme, and we'll see if it actually works. But let me just explain what's behind this strange thing. This goes back to this was not in the period 1925 to 32, this is a little bit later. This fellow, Majorana, in Italy, came up with he came up with a strange conclusion that now we can reinterpret in the following way. I've got an orbital, which is a box that can be empty or filled, and the qubit information is whether it's empty is down and filled is up, for example. The qubit information will be making a box which was somehow a mixture of the two. But the Majorana thing is that you can actually, by an analog to what I found in the spin chains, is you can actually break this orbital into two half orbitals, which is a really strange concept. And when you break it into two half orbitals, the information about whether it was empty or filled, is hidden. Let's go back. Hidden here. So in the entanglement streak between the two things, and so the half orbitals are called Majorana zero modes, and they can actually be made not just in the quantum Hall effect, where that was initially thought you could make them, but just by combining semiconductors with superconductors. And this is at the heart of this Microsoft attempt to build a topological quantum computer. So here we have this box, which can either be empty or filled. When I pull this apart into two halves, the information about whether it was empty or filled is in the intermediate part. So it looks exactly the same to the outside world, whether they initially started as empty or filled. Oops. Okay. So the information is very well hidden. And in fact, the only dangerous part of the whole procedure is pulling the things apart where when you put the information in initially, the read-in aspect, and then to read the information out, you have to join them back together again. But you don't necessarily join the same half box with its partner, right? You move the half boxes around, and maybe you join different other half boxes together. And then when you join them together, you find the measurement is, are they empty or filled? And you can tell that by looking at them, whether they're empty or filled when they're joined. So this operation of moving these things around each other disturbs the quantum information which is hidden everywhere in the region surrounding these dots. And this kind of scheme, it doesn't require any kind of delicate timing as you need for standard qubits. However, Microsoft and others haven't yet managed to get this system working. But on paper, it works fine, like fusion works very fine. But it's, again, an example of the strange things that quantum mechanics allows, and we're trying to exploit. Okay, so let's see. So as I say, quantum mechanics has given rise to all kinds of beautiful dreams of future technologies. And certainly the standard qubits are approaching, which will give you a technology we call NISQ, or noisy intermediate scale qubits. There the system is essentially that you have to, if your quantum computer isn't properly protected against degradation with the environment, you have to start off with, say, 10 copies of everything, and you can tell by looking at it if one of the copies of the calculation has become different from the others. You can't ask what's happening during the computation, otherwise you ruin it, but you can sort of see if one became bad, then you throw it away. As long as you've got enough copies of the computation at the end of the day, when you reach the end, to get the same answer at least twice, you're in business, right? But so far, you always will end up losing information. This system would give you quantum information protected while you're actually doing the computation, and your losses would only occur at the read-in and read-out stage. Okay. So anyway, whether or not this happens is some kind of quantum technologies are certainly emerging very rapidly. The Kitaev chain, or the Majorana zero modes, is as follows: that you can formally write an electron operator as a complex number, which has a real part and an imaginary part, and I can think of splitting the electron orbital into its real part and imaginary part. The Kitaev thing works that I can now rejoin the orbitals by joining back together the real part of one site and the chain to the imaginary part of the other one, and out of this I will end up with a free half orbital at the end, which is a much more remarkable version of the thing I found years ago in the magnetic chain. And these are these Majorana zero modes, which are at the heart of the Microsoft idea. Anyway, so this is just one of the current approaches to quantum computing. There's plenty of other qubits which are getting better and better all the time, and error correction codes are being devised. So you would actually be using 10 qubits to make a virtual qubit that you sort of can try to correct errors. So I don't know what will finally emerge, but I'm certainly sure that we'll learn a lot of new things in the second quantum revolution. And it's not just qubits, not just quantum information is the thing. The qubit is the delicate coupling of the qubit to the environment. It can be used for very high precision sensors. And the thing that we're going to see in the next year or two is a lot of developments in high precision sensors for measuring the environment. The quantum, for example, nitrogen vacancy in diamond is a very sensitive qubit, and we can use this to measure both magnetic fields very strongly, and with cold atoms we can we can watch them falling and measure the gravitational field. And there's both for measuring what goes on in the brain and maybe on a much finer level than we can do right now, or geolocation, looking at fingerprint of the Earth's magnetic field at every point on the surface. There's going to be a lot of new developments, not yet with the quantum information, but with just the application of the qubits to quantum sensors. So finally, lots of different kinds of people need to collaborate to work out what quantum mechanics is doing. I'm a toy model builder, building simplified models, but we need people who understand the mathematical principles underlying the weird stuff that comes out of the toy models, and we need the material scientists to actually build these things and turn them into reality. And finally, I get a motivational message. So the things I described, the discoveries were kind of luck, basically. They're being in the right place at the right time and recognizing that something amazing has shown up. And so I say this is a motivation message for anyone involved in basic research. So for the graduate students, you know, you don't have to be a kind of super brilliant genius to get a Nobel Prize, because there's plenty of super brilliant geniuses, right? You need the luck that your research path takes you close to something that no one knew existed, and you need the preparation that you noticed some anomaly and got interested enough in it to see, my gosh, that's something unexpected, and then you need to probably fight to convince people that this is what you found something new. But anyway, so there you are. So I say, if you want to get one of these, everyone's got a tiny, tiny chance if you're doing basic research. And if you have luck, make use of your luck. Thank you.
Thank you, Professor Haldane, for sharing your insights. Please take a seat at the front for the Q&A segment. Now, to moderate the Q&A segment with Professor Haldane, I would now like to invite Associate Professor Yang Po from the School of Physical and Mathematical Sciences up on stage. Professor Yang Po, please.
Okay, thank you very much for a very interesting talk. So I'm just the moderator here, so now the floor is open. I'm sure you have a lot of questions for Professor Haldane, so we do have microphones around, so if you have any questions, just raise your hand or just grab a microphone. Okay? Who won't be the first? Yes, please.
You mentioned these the spin one chain and the quantum Hall effect. So these are different from the topologically ordered states like the fractional quantum Hall and Majorana, right? So you mentioned those also have entanglement, and I'm wondering what's the potential for the integer quantum Hall entanglement to be used for quantum computing? Is that useful, or is it not entangled enough? This like short-range entanglement or something?
To be able to actually hide the quantum information, you need not just quantum Hall or fractional quantum Hall. You need these so-called non-abelian quantum Hall states, where the third generation of these things, which allow you to hide the information. And the key, the Majorana zero modes turned out to be available in other contexts too. For example, the superconductor coupled to a semiconducting chain with a high spin orbit coupling, which is the Microsoft thing. So what these things are basically saying is that quantum mechanics has these possibilities that it has taken time to understand that they're there, and now we understand they're there. We're trying to find a way to bring these things to new technologies. But quantum mechanics, just as that I discussed very briefly, the sensor technology is going to revolutionize things. For example, we can measure the gravitational field of the Earth much more precisely by watching little atoms drop in the magnetic field. And so that's going to have tremendous implication for finding mineral resources and things. A much, much finer thing than the classical methods. And I believe that this discussion about a backup for the GPS system, people worry about what happens if the GPS somehow gets jammed by whatever, by some malign or forces, or just breaks down. The planes, it turns out if you can measure the fingerprint of the very fine details of the magnetic field of the Earth, which can be measured by a plane carrying these ultra precision devices, is apparently like a fingerprint. So you need AI to tell you to go through the fingerprint map of the Earth to tell you where you are. But these are kind of very surprising things that.
Okay, how about for quantum sensing, the quantum Hall effect, integer quantum Hall effect? Do you see any potential from the integer quantum Hall effect, these simpler topological states, to be applied to quantum sensing?
I don't know I don't know for that, but
I see.
The edge states are interesting, and there's been some discussion about one of the big problems is interconnects in the energy being used in the data center. About 25% of the energy is lost in the interconnects. If you could improve the interconnects between things or get rid of, and some people have thought about these topological edge states might be a way to do that. So I guess we have to dream quantum dreams, and we have to see if they can be, and some of those quantum dreams will eventually get turned into remarkable new technologies. And so this is what I think the near future brings, much more truly quantum technology into play. Yeah.
Thank you.
Thank you. Okay. Next question.
Hi, Prof Haldane. I'm Tian. I'm currently a postdoc at NTU. I'm particularly interested in one of the applications you shared just now, which is the nitrogen substitution in diamond that can act as a qubit for sensing applications.
Yeah.
So as currently I'm also working on studying the defects in materials and how they can change the material properties, although not particularly on the qubit applications. So I'm using DFT modeling to study all these properties. But I'm just wondering, what are the properties or patterns that you can see to determine why whether a defect in the material can actually act as a good qubit? And do you see any patterns or properties to look at to see these kind of applications?
Yeah. Well, I'm not an expert on these things, but basically the two-level system in quantum mechanics is just a fundamental thing. You can find all kinds of examples, and all the different kind of attempts at building quantum technologies. Many of them everyone has chosen a different scheme. There's the Rydberg atoms, as I showed a picture of one. Those are arrays of these things can be addressed individually with a laser, and those are very promising for some things. Then there's superconducting qubits called transmons, where you have flux going through a little loop. There's people trying to use the photon itself for the qubit. Anything which the qubit is basically the two-level system. In fact, if many people have read the Feynman lectures, Feynman of physics, and he actually advocates teaching quantum mechanics starting with the spin, the two-level system, which I kind of agree with. So the two-level system is this fundamental unit of quantum mechanics, and it's really come to the fore in all these different attempts to understand what kind of entanglement you can get between systems of qubits. Yeah. So the nitrogen vacancy in diamond is a very promising one, and it's certainly got a big future as a sensor.
We also welcome people who are not doing research in physics to ask questions. So anyone can ask questions. Yes, we do have a few. Great. Over there. Yeah.
Hi, Professor Haldane. I'm a first-year PhD student. I feel
In
confused.
physics? Are you a PhD student in physics?
I'm in Triple E, and my
Triple E, okay.
field is quantum sensing, based on NV centers. I'm very confused what to do for my research. So someone tell me that if you don't know your research directions, you just read a lot of articles and the ideas will come. So I want to ask you, what will you do if you don't know your research direction?
Okay, very good. Yes, actually, science is a very social human subject, I think, and discussion. And one of the best ways for getting ideas and developing your ideas is through discussing them with people, right? And having a group of people which you kind of try to understand something. If you're trying to understand the earlier literature, for example, it's a lot easier to discuss it as a kind of group rather than sit alone in your study, kind of trying to understand what on earth this stuff means, right? And to find a research direction is always a challenge. I recommend people go to lots of seminars when you're starting out, at least, just to expose yourself to different things that you didn't know about. And sometimes if you see some connection between the things you know about and what's being discussed, that's the most fruitful way to find a new research direction and to take stuff that you know and try to push it in a direction that the previous people working on that haven't done.
Do you mean you just communicate with people from different research area?
But also, or just you've got your nitrogen vacancy, right? Look, dream up something you can do with it, right? I mean, basically, they're the thing it's a very sensitive measure of the magnetic fields, right? But then, I guess the difficulty there is you can't. I don't think you can make a nice array of nitrogen vacancies. You have to kind of take the ones that you find in the diamond, right?
We can also ask, have you ever had an extended period of time in your research career that you don't know what to do? Ever?
I think everyone does, yeah.
Yeah, I think that's the main message also. In research, it's very common, so don't worry too much about it. And follow the advice from...
And you get ideas from listening to seminars, talking with people. Yeah. And even just thinking about...
If you're working on something, you're very busy, you don't have the time to expose yourself to many different ideas. Now, if you don't know what to do, it's a perfect time to just go to different seminars and try to absorb as much information as possible. So it's not a bad thing.
Okay, thank you.
Okay, good. Another question here?
Hello, Prof. I'm an undergraduate, and I don't know much about quantum physics, but I want to ask about your views on quantum foundation. I know there are some groups working on quantum information. There are still people working on quantum foundation. They say that may make some changes. Maybe our new understanding about quantum foundation, will they bring some practical effect on the technology and and do you think quantum foundation will be part of the second quantum revolution? Is it a good area to jump in?
it's not clear because people spend a lot of time thinking in the past about quantum foundations and trying to interpret quantum mechanics, many world theory and stuff like that. But in the end, the modern developments come from actually trying to do something with the quantum mechanics, right? In a sense, unless some experiment shows that quantum mechanics needs modifying in some fundamental way, and no such experiments have yet come to light, we sort of need to kind of accept quantum mechanics, right, without worrying too much about what it implies about the universe or free will or anything. These kind of questions in the past never led to anything. Now, I guess the idea that John Bell's idea to actually try to turn Einstein's thought experiment into a much more precise experiment, which would actually rule out something had an important effect. Because in the past, people didn't really think too much about entanglement. I guess they said, just shut up and calculate rather than. But the quantum foundations aspect is difficult, right? But what we know about the universe keeps changing too, right? I mean, 15, 20 years ago, there was we didn't have any idea about dark energy. Dark matter was also came up. So I think without some concrete experimental question to answer, the foundational aspects don't seem to be leading anywhere, right? So I think the progress now is going to come from doing observations. Maybe we have to understand more precisely what happens during the measurement process, right? But to actually think that, do I get entangled with the qubit when I measure its properties? I mean, that's probably not, that's a kind of interesting theoretical question, but it doesn't really have an effect on the actual experiments, right? So I think actually doing something with the quantum mechanics, and we'll learn more about what's possible with quantum mechanics through actually doing stuff, I think, rather than thinking about it.
Thank you.
Thank you. Okay, yeah, we have maybe first and second, yeah. Over there, there's a question over there, yeah.
Thank you, Professor Haldane. I actually went to one of your lectures a few years ago and asked for your signature, but this year I've heard many new things from you. And so one of the things I have is on... Oh, do I stand up? Oh, okay. Yeah. So one of the questions I have is on the Majorana patterns that you've mentioned previously and how it can be developed into a quantum computer. So when I was listening to your lecture earlier, I had a question because you mentioned about Microsoft trying to make a quantum computer out of it, and to me, it was because my understanding of the Majorana zero states is that you split them to half and then you can overlap them to create patterns, if I'm correct. So my question is, if you want to make it into a quantum computer, then I assume you need multiple qubits to do so. But if the pattern is done by, so is the pattern created or is the protected qubit created by modifying each individual qubit? Or is it done on a macro scale? So example, you modify like a bunch of them at once. But in this case, then it leads to two additional questions, which is that if it's a macro transformation, then how would you ensure that all of the things align such that it is able to achieve the effect? And if it's for an individual alignment to store the data, then how would you ensure that each individual alignment would coupled or entangled together? The mic is not working.
It's a very technical question.
Yeah,
so.
It's a technical question, basically.
The Microsoft Majorana thing is the shape of an H. They call it a quartet or something. But basically, to make a qubit, you need at least 4 Majoranas because you can't mix states you can't mix fermionic states and bosonic states. So with just two things. There's a Fermi number. If you have 4 Majoranas, you've got 2 orbitals, and they can be either both empty or both filled. That's 1 qubit. Or if the number of electrons in the system is odd, they could be 1 empty, 1 filled, and vice versa. So the elementary object is 4 Majoranas to give a qubit. In principle, you could have, each time you add another pair of Majoranas, you get more. The architecture that Microsoft are talking about, although they seem to mainly be making YouTube videos about it, but it's like a shape of an H. You've got the 4 Majoranas on it. The important thing is that the Majorana wave function kind of leaks in. The Majoranas have to be separated on a scale that's large compared to the exponential penetration into the thing, and it's not. The problem with people's attempts to make the Majoranas have been generally not being able to get the system big enough. But it's a question of making as you pull these things apart, there's entanglement. But you need to have them pulled apart sufficiently far. But we'll find out actually whether we get working qubits out of this thing or not, and whether the topological protection works. Now, I mentioned there was this, Quantinuum who would do this stuff with a racetrack full of ions. There's actually been simulations of the topological qubits done in these things, and so on paper it works, and simulations work. Now in real life, there's all kinds of other things like an electron coming in, leaking into the system from somewhere else. That's called quasi-particle poisoning. And just like in fusion works extremely well on paper, it works in the sun, but there's always kind of technical issues in confining the plasma or whatever. So we don't yet have a fusion technology, and we don't yet have topologically protected qubits, but it's a promising direction, and we'll find out, whether it works. I mean, it may just turn into it may just provide a theoretical basis for virtual topological qubits for error correction or something, but we'll find out.
I guess due to the constrained time, we have one last question over here.
Hi, Prof. Do you have any kind of advice for us students who is looking for a proper group to continue PhD study? And yeah, I'm the student who was working on theory, open quantum system, but I gradually found that those kind of things is becoming a kind of digital experiment. So I want to do some real physics. But I found that those experiment group doesn't accept a guy who doesn't have any experience. So I'm wondering if you can give us any advice. Thanks.
Well, just be curious, I think. And, I think just trying to discuss what you're doing and go to seminars and try and I think the more you understand what you're doing, the more likely you are to see how to make it progress. You can't just say you take a set of papers and you say, okay, I'll take whatever they say as true and try to build something on that. You need to try to understand really the fundamental basis of what you're trying to do, and that can help you see some places, see some direction to go in, I think. I'm not sure that answered the question.
Yeah, do you know what you are passionate about when you're trying to look for a particular group?
Yeah, I think my research interest is in quantum simulation, and especially the non-equilibrium. I think it's promising and rewarding on this topic.
There are lots of important questions, and you want to find a question that you can be passionate about and really interested
Ladies and gentlemen, once again, can you please give our professors another round of applause? May I now invite Professor Chiba up on stage to present a memento. Professor Haldane on behalf of the IAS and NTU. May I also invite Professor Sun and Professor Yang go up on stage for another picture. Audience members, please remain seated first while we allow our distinguished guests to leave first. Once again, thank you, distinguished guests, as well as all our audience members for joining us today. This brings us to the end of the IAS